Hello and welcome. A few years ago, I served as a volunteer on a construction site in Ensenada, Mexico. We were building a house that had some unusual angles. It was kind of unusually shaped in its roof, and no one really knew how to proceed as far as what lengths of boards to cut in order to get things exactly right. I decided to take on this part of the project as my own, and I took some significant measurements, did some calculations on a piece of paper, and gave the specifications for what needed to be cut to the carpenters on site. To everyone's amazement, when the boards were set into place, they slid in perfectly. What I had used wasn't magic, it was simply trigonometry. When you know the angles of a right triangle, you can calculate the ratios of the sides. And when you know the sides of a right triangle, you can calculate the angles of the right triangle. This forms a very useful set of tools that has applications in scale drawings and architecture and construction, to electronics, and definitely animation and computer graphics, especially when those computer graphics involve 3D animation. So I'm hoping that this, in our last topic together of things that we need to cover, I'm hoping that this can be something that you will find useful in your career, or at least will tickle your fancy, or in some other ways broaden your mind and enhance your knowledge base. But before we broaden our mind, we have to empty it first, and so let's take some time to do just that, to bring ourselves completely into the moment, to empty our mind of thoughts, and to make it so that we are completely ready to spend our time together with each other. Take some time for that. Welcome back. Well, you may have noticed on your calculator that there are 3 buttons that are kind of strange, and you may have wondered what those buttons are for. They look like they have the words sin, cos, and tan on them. Sin, cos, and tan. Those are your trig functions on your calculator. You might also see in some other places sin with a -1 sitting in just to the upper right of it. Same thing with cos and tan. Those are inverse trig functions, and so essentially these are some buttons we're going to be using an awful lot in today's lesson. I hope you've got a calculator with you that has some trig functions on it. If not, then you can actually, it's not too difficult, I've found, to download a free calculator onto your phone that employs enough scientific functions on it that these trig functions are included among them. Also, make sure that if your calculator has some statement above as to what mode it's in. I've discussed at least in some of my classes with you that the calculator can be set to accept angle measurements in degrees. That's what DEG means if that's lit up near the top of your calculator. That can also be set to radians, and we've talked about radians in some of our previous discussions together. But let's make sure for our purposes that it's set to degrees, and so that our activities, as you're working on today's activity, you're able to do it properly. Here's an example of how we can use trig functions. Let's say that you're a person who is sitting in the water. It's kind of strange, I've got a person standing in the ocean there, but let's just say that they're sitting in a boat somewhere and they're wanting to calculate the height up a cliff to the top there. And they know that they are 250 feet out from the base of the cliff. And when they look at the top of the cliff, the angle that's being made with the top of the cliff is an angle of 40 degrees. They would use something called a ceilometer, similar to the sextant that was used by ships when they were crossing the Atlantic Ocean. You could figure out what latitude you were, because the farther north you were, the more northern hemisphere constellations and you could see in the night sky, and you could measure the angle that the North Star was and things like that and figure out what your latitude was. So finding the angle measure from the horizontal is nothing new to people who work in the sea and surveyors and things like that. So, but it's a ceilometer. That's the term that we would use today for that kind of a device. And we can see in this instance that the angle measure is 40 degrees. The angle just to the left of me here at the base of that cliff, that's a 90-degree angle. That indicates that we're working with a right triangle here, and so we're able to use trigonometric functions as one of the tools in our arsenal. Well, 40 degrees isn't a special angle from any of the stuff that we've done before. We've worked with 45, 90-degree triangles. We've worked with 30, 60, 90-degree triangles. Those have some special relationships among the sides, but this one, nothing special about 40 degrees. And so what do we do? So what do we do with this triangle here that has an angle that's nothing special in terms of the special right triangles that we've been working with? Here's a place where we make use of trigonometric functions. Here's another example of a right triangle here. I've just extracted it and written on a sheet of paper here. This is a different triangle than the one that we saw on the previous slide there. This is one that's got a hypotenuse of 8.235. It's got obviously a right triangle on the opposite side of that. You can see that just to the upper left of my head here. It's also got two legs of the right triangle. Remember, we call these things legs, 3.4 and 7.5. It's also got two angles, and we know that one of the angles is obviously 90 degrees. If we know that the second angle to the far left there is 25 degrees, all the angles have to add up to 180, which means that all three of these angles are supplementary. Remember that term? Since one of the angles is a right angle, the other two angles have to take up that remaining 90 degrees. They have to add up to 90. So these two angles here have to be, what's the term? Complementary. These two angles are complementary, so they add up to 90 degrees. So if you know one as being 25 degrees, then the other one has to be 65 degrees. It has to add up to 90. So that's one connection that you can make with this right triangle here. But let's focus specifically on the 25-degree angle here. And what is a trig function? It's just a number that you get when you take an angle measure and hit the button. Sine, cos, or tan. Sine means sine, cos is the abbreviation for cosine, and tan is the abbreviation for tangent. So when you enter in a degree measure and hit that button, you're getting a specific ratio between sides. And here's what the ratio is. For sine, we get a specific ratio, and to illustrate this, I've got the hypotenuse showing up in green, and I have the two legs here in yellow and blue. Now, in relation to the 25-degree angle here, the yellow side is opposite that angle. Hopefully you can see that. The angle is way over there on the left. This side is on the right. It is opposite that angle. And in relation to the angle that's 25 degrees, we would say that the blue side is adjacent. It's next to that angle. It's not opposite to it. It's next to it. It's adjacent. So those three words, hypotenuse, opposite, and adjacent, are going to be prolific throughout our presentation together here. So what is the sine of 25 degrees? It's whatever number you get when you take the opposite side, that's the yellow part, and divide it by the hypotenuse. As it turns out, for every 25-degree angle in a right triangle, you get the same ratio between those two sides. Always, always, always. And so what is that ratio? Well, it's whatever you get when you hit 25 on your calculator and then the sign button. By the way, if you've got a more advanced calculator, you might have to hit the sign key first and then type in 25 and hit enter in order to find out what that number is. It's going to be some kind of decimal between -1 and 1, or in our cases, somewhere between 0 and 1. And you can see in this case that the sine of 25 degrees here is 0.41287. We could get that from taking the first number there in yellow and dividing it by the green number, or we could get that by finding out the sine of 25 degrees on your calculator here. Cosine is the exact same thing, except instead of looking at the opposite side over the hypotenuse, we're looking at the adjacent side over the hypotenuse. So it's not the yellow over the green, it's the blue over the green. So for this one, you can see it's a similar ratio, but it's 7.5 divided by 8.235. And if you do that division on your calculator, you'll get 0.91075. You will also get 0.91075 if you find out what the cosine of 25 degrees is on your calculator. So once again, that ratio is always true for every 25-degree angle. Always, always, always. Lastly, what's tangent? Well, this is the one that does not use the hypotenuse. We had opposite over hypotenuse, we had adjacent over hypotenuse. The third one would be opposite over adjacent. So what we do here is we don't involve the green side at all. We make use of the yellow and blue sides, and it's yellow divided by blue. So it's the opposite side divided by the adjacent side. And when we do that here, we get a number like 0.45333. That's what we get when we divide those two numbers out. It's also the number that you'd get if you were to take 45 and hit the tangent key on your calculator. So you can summarize all of these things together with a single acronym here, SOHCAHTOA. What this means here is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If you get that, you've got today's lesson. You know what to do. So really today we're just going to be doing this over and over and over and over and over again to find out some values for lengths of sides. Also we'll be doing it in reverse as well to find some values for angles here, but we'll be using the same SOHCAHTOA mnemonic here for remembering what sine, cosine, and tangent are. So SOHCAHTOA, remember that one. Here's how this works here. Let's say I've got a line, and I'm going to move this line upwards just a little bit here. All right, so what I've got here is a right triangle, and this angle here is 30 degrees. As it turns out, let's assume for our purposes here that the length of the hypotenuse, the length of this line that was moving beforehand, is just 1 meter, 1 foot, 1 inch, whatever. We'll just call it 1. And that means that we'll measure the sizes of the other sides in relation to that hypotenuse, which has a length of 1. So what's the length of this side that's actually just above my head here going to be if the hypotenuse is 1 and the angle over there is 30 degrees? As it turns out, the answer is 1/2. This side is always half as big as that one. You actually know that from one of our previous videos here. Remember, this is actually a 30, 60, 90 degree triangle, and we knew there was a 1:2 ratio between this side and the hypotenuse for a 30, 60, 90 degree triangle. So to some extent, this is nothing new. In addition to that, the length of this side is always going to be the square root of 3 over 2. If that angle is 30 degrees and this hypotenuse has a length of 1. So the ratio of the opposite over the hypotenuse is 1/2, 1/2 to 1, or just 1/2. And the ratio of the adjacent side, that's right next to me here, is square root of 3 over 2 divided by 1. That's just the square root of 3 over 2. That's always, always true. In addition to that, what do you think the tangent is going to be? Well, that's opposite over adjacent. Which one's the opposite side? Well, it's the 1/2. And what's the adjacent side? Well, it's going to be square root of 3 over 2. Okay, so what's 1/2 divided by square root of 3 over 2? That's a little bit tough to do, but if we take that ratio, multiply the top and bottom by 2, that's going to cancel out that 1/2 on top. It's also going to cancel out that 2 underneath the square root of 3 there, and so we're just going to have 1 on top and square root of 3 on the bottom. 1 over the square root of 3 is the tangent of 30 degrees. We can proceed on from there. This was a 30-degree angle. Let's make it a 45-degree angle here. Okay, so here's our triangle. This is 45 degrees. Once again, the hypotenuse, we're just setting at 1 here, and so all of the other side lengths are going to be in relation to that hypotenuse length of 1. All right, so if the hypotenuse has a length of 1 and the angles are 45 degrees, actually both of those angles should be 45 degrees, shouldn't they? Then what's the length of the other two sides? Well, as it turns out, maybe you remember this from a previous video, 45, 45, 90-degree triangles. In order to go from one of the legs of the triangle to the hypotenuse, we multiply by the square root of 2. That means in order to go from the hypotenuse back to one of the legs, we don't multiply by the square root of 2, we divide by the square root of 2. So each one of these is 1 divided by the square root of 2. It's about 0.71, so on and so forth. And so this is one of our previously known triangles here, and again we can calculate the sine and cosine and tangent of 45 degrees based upon this information that we already know. The sine of 45 degrees again is opposite over hypotenuse. That's the so in SOHCAHTOA, isn't it? Opposite over hypotenuse. And so we have 1 over the square root of 2 divided by 1. Well, that's just 1 over the square root of 2, isn't it? Similarly, what's the cosine of 45 degrees going to be? That's the ka in SOHCAHTOA. Cosine is adjacent over hypotenuse. What's the adjacent side? Oh, it's the one just to the left of me here. It is 1 divided by the square root of 2, again over the hypotenuse. 1 divided by the square root of 2 over 1. Well, that's going to be the same thing as before, isn't it? So the cosine of 45 degrees is the same thing as the sine of 45 degrees. It is also 1 over the square root of 2. Lastly, what's tangent? That's the TOA part of SOHCAHTOA. Tangent is opposite over adjacent. That's 1 over the square root of 2 divided by 1 over the square root of 2. We have the same thing in the numerator and the denominator, so what is the tangent going to turn out to be? It's going to be 1. The tangent of 45 degrees is just 1. Let's proceed on from 45 degrees up to 60 degrees. And let's see how things pan out from there. Again, we're going to have a 30, 60, 90 degree triangle here, so these ratios should be familiar from one of our previous videos here. Again, the hypotenuse is just going to be 1, and so what is the length of the side that is opposite the 60-degree angle? Well, again, this is going to be the square root of 3 over 2, and the length of the side nearest to the 60-degree angle, the one adjacent to it, is going to be 1/2. Once again, see if you can recall these ratios, these connections, these relationships from our previous studies of 30, 60, 90 degree triangles. Check your notes on that. This should make sense based upon your notes from previous discussions here. Okay, well, how do we calculate sine, cosine, and tangent of 60 degrees based on what we're seeing here? Again, sine is opposite over hypotenuse. That's the so in SOHCAHTOA, opposite over hypotenuse. So the sine of 60 degrees is the opposite side. That's the one directly above, well, almost directly above me. It's square root of 3 over 2 divided by the hypotenuse, which is just 1. So that's just the square root of 3 over 2. The cosine of 60 degrees, that's going to be adjacent over hypotenuse. That's the ka in SOHCAHTOA. The adjacent side is, well, it's not that one there, it's one just to the left of me, isn't it? It's 1/2. So 1/2 divided by the hypotenuse, which is 1. So 1/2 divided by 1, well, that's just 1/2, isn't it? The cosine of 60 degrees is 1/2. Lastly, what's the tangent? Tangent is opposite over adjacent. That's the TOA in SOHCAHTOA. So how do we do this here? The opposite side is square root of 3 over 2, and the adjacent side is 1 over 2. Well, that's going to be a mess, isn't it? But again, if we multiply by 2, top and bottom on that fraction, which remember we can always do to simplify a fraction, we can multiply top and bottom by 2. That's going to cancel out that 2 underneath the square root of 3 on top there. It's also going to cancel with that 1/2 on the bottom, just make that 1. So we're going to get the square root of 3 over 1, which is just the square root of 3. The tangent of 60 degrees is the square root of 3. Lastly, what happens when we start to get a triangle that's really tall and skinny? Well, that's an instance in which this angle is, well, theoretically it can't be 90 degrees, but we can get pretty close to 90 degrees, almost straight up here. Well, what happens when the angle gets really, really close to 90 degrees? Well, if we take a look at, again, the hypotenuse being just 1, you can see the opposite side here is almost the same as that hypotenuse. The tilde here means approximately, or just about. So that hypotenuse is pretty close to 1, so that side that's right next to it is also getting pretty close to 1. How about the side that's to the left of me here? This teeny tiny little side. That one's getting smaller and smaller, isn't it? It's getting closer and closer to 0. So let's ask the question, what is sine and cosine and tangent approach as we get an angle that's closer and closer to 90 degrees? What are we getting closer and closer to for our sine and cosine and tangent? Well, for the sine is opposite over hypotenuse, so that's 1 over 1, or just 1. So sine gets closer and closer to 1 as the angle gets closer and closer to 90 degrees. All right, so cosine, that's the adjacent side. That's the one just to the left of me here. That's the one that's getting really small, close to 0. That's 0 over 1, so that's pretty much 0. So cosine gets closer and closer to 0 as that angle gets closer and closer to 90. What happens to tangent? That's opposite over adjacent. 1 over 0. What's that? Do we remember? Can we have a 0 in the denominator? What do we call it if we have a 0 in the denominator? We say that it's undefined. Tangent gets closer. Actually, it shoots off to infinity as you get larger and larger angles there. But once it hits 90 degrees, it becomes undefined. And let's actually switch from angles that are very, very big, in other words, close to 90 degrees, to angles that are very, very small. So this one was previously almost vertical. Let's make this one almost horizontal, just a little bit above the horizontal here. So this angle here is pretty close to 0 degrees, we'll say, just a little bit above 0 degrees. And again, our hypotenuse is 1, but let's ask ourselves the question, what's the length of these other two sides here? And what are they getting close to, more to the point? Well, the one that's just to the left of me here is getting close to the same length. It's getting close to lining up with that hypotenuse, isn't it? So it's pretty much getting closer and closer to 1. The one that's directly above me is getting shorter and shorter and shorter, and that one's pretty much going just to 0. Well, based upon this, let's ask ourselves the question, what are sine, cosine, and tangent becoming as our angle is getting smaller and smaller and smaller? Let's find out here. So sine is opposite over hypotenuse. So again, opposite is that really small side just above me. It's getting close to 0. That's 0 over hypotenuse, 0 over 1. So the sine is getting closer and closer to 0. So as the angle goes from 0 to 90 degrees, the sine goes from 0 to 1. Let's take a look at cosine here. Cosine is adjacent over hypotenuse. Adjacent is that side to the left, which is getting closer to 1. The hypotenuse is 1, so that's 1 over 1, and so the cosine here is just 1. So as we go from an angle that is very, very small, like right here, to one in the previous slide, which is getting close to 90 degrees, the cosine goes from 1 to 0. It does the reverse of what sine is doing. Sine goes from 0 to 1, cosine goes from 1 to 0. Okay, lastly, what does tangent do? Tangent is opposite over adjacent, so that's the 0 side divided by the 1 side over here, well, the almost 1 side, I should say, and so that's 0 over 1, which is just 0. So tangent, in going from 0 degrees to 90 degrees, goes from 0 to undefined. So let's actually take some time here to find out what these ratios are for all these different angles here. So what I'd like you to do is to make use of your calculator to find out what the sine of 0 degrees is, what's the cosine of 0 degrees, what's the tangent of 0 degrees, and then do that for the other angles as well, 30, 45, 60, and 90. So this will be, I think, very useful for you in getting comfortable with using your calculator to calculate these trigonometric functions, which, given an angle, will give you a ratio. So take some time to do that. I should also mention at this point that you've got a place up here near the top for filling in all of these trig functions here. Not all of them are represented on the screen at this point, but they will eventually all be filled in, but just notice which ones are listed there and fill in the appropriate part accordingly. Welcome back. Well, hopefully this was a useful exercise in getting you comfortable with using your calculator for calculating trigonometric ratios based upon angle measurements. In addition to that, perhaps you noticed a pattern in the values of sine versus the values of cosine. Notice what the value of sine does as we're going from 0 to 90 degrees. It goes 0, 0.5, 0.7071, 0.8660 to 1. Notice what cosine does. It does the absolute reverse of that. It does 1, 0.8660, 0.7071, 0.5, and 0. It's the exact opposite. That's actually why historically these two functions have been given so similar names, sine and cosine. One is kind of the co-pilot of the other, so to speak. So they're very, very related to one another. Now, I indicated those angles on your sheet here as being areas that were shaded in. Those are kind of the first sets of angles that you can use to fill in those values of those trig functions there. Now let's do the same thing for some of those more lightly shaded areas. Fill in those values of sine, cosine, and tangent for those angles. So take some time for that. Welcome back. Well, this is another set of trigonometric ratios that you're able to get from placing a set of angles into your calculator for calculating trig functions. Again, hopefully you kept your calculator in degree mode when you were entering in these values. Otherwise, it might have assumed that you were putting in 20 radians rather than 20 degrees when you were putting in your degree measures here. If you got strange values when you were putting in when you were finding these sine, cosine, and tangent functions. That's probably the reason why you were doing that. It's probably the reason. If you're getting strange values for all of these trig functions when you were putting in your degree measures, that's probably the reason for it. Now we saw with all of these trigonometric functions that if we put in the value of an angle in degrees, the measure of an angle, 56 degrees or whatever, we would get the ratio of two sides, one to the other. Turns out we can also go in the opposite direction. If we put in the ratio of two sides and take the inverse trig function, we can get back to what the measure of the angle is. Here's an example. Take a look, not at the one in the upper left there, let's go one down and take a look at the inverse sine of 0.5. In this case, we're not entering in an angle measure. We are entering in a ratio of two sides. We're still making use of SOHCAHTOA. For the sine, it's opposite over hypotenuse. So when we put in a value of 0.5 here, what we're saying is that the ratio of the opposite side to the hypotenuse is 0.5. That opposite side is half as big as the hypotenuse. Turns out we can find out what the measure of this angle is once we have that information. So what we do here is we're putting in that inverse, that ratio of 0.5, and on your calculator you can actually to some extent see it. This is a popular way of doing it here. I'm going to use my mouse so that you can see it here. Above each one of these buttons, it's not uncommon to see among calculators the cosine -1. That's an inverse cosine. That means this is the function that you use when you've got a ratio and you want to go back to an angle. That's the inverse of what we've been doing, hitting the sine, cosine, and tangent buttons. We were putting in an angle and getting a ratio. Now we're putting in a ratio and getting an angle. And in this case, it's inverse sine that we're wanting to do. So there's usually some colored button in the upper left-hand corner that you hit that is the same color as however this is written above here. Usually it's in green or it's in red or something. You hit that button and it makes available to you all of the functions that are not written on the buttons but above the buttons. So you hit that button, it's usually in the upper left, and it makes available to you, it's basically your entire keyboard changes. It's almost like the shift key or the control key or the alt key on your keyboard. It makes available to you a whole different set of functions. So when you hit that button and then hit this button, then you're not doing the sine, you're doing the inverse sine. So try that with 0.5 and let's actually see what you get here. First of all, let me just say here, for 0.5 you should get 30 degrees. See if you've got that. If you get something like 0.5 something something something, that probably means that your calculator is in radians. Again, you'll want to check to make sure that it's in degrees, but it should come back with 30 degrees. Again, if this is a scientific calculator, you might have to do inverse sine first and then type in 0.5, hit enter, and see if you get 30 degrees there once you're done. So in addition to that, as you can see, the inverse sine of 0 is 0 degrees. That's a 0 degree angle. That's kind of impossible, isn't it? It's not really a triangle at that point, is it? But take some time to do some of these other ones. In this case, once again, you're not finding ratios between sides. You're now using ratios between sides to find angles. Take some time for that. I should also mention at this point, I've got a lot of slots of information here for the inverse trig functions for you to fill in on your activity sheet here, and not all of them are represented on the screen, and so but they will eventually be filled in. So just notice which ones are appearing on the screen right now and fill in your paper accordingly. Welcome back. Well, it's a lot harder to predict what's going to happen when you have these rather unfamiliar ratios among sides, but so it might have been a little surprising to you when you saw these very familiar degree measures here, consistently 0, 30, 45, 60, and 90 in all three columns here for sine, cosine, and tangent. Well, there are a bunch of rows of information to fill in here on your activity sheet, not all of which were covered in this first slide, and so you guessed it, you have some additional ones to fill in here to complete all of your entries here on your activity sheet. So we've got inverse sine, inverse cosine once again, inverse tangent for a series of common ratios here that you can see, 0.2, 0.4, 0.6, 0.8. You can see here that the inverse, the ratio for tangent that we can put in to the inverse tangent can get above 1. That can actually get rather large, as high as 10, or I think in some of our previous calculations we calculated it as being above 50. So tangent can get very, very large as you're getting closer and closer to 90 degrees here, and so you'll find that that inverse tangent value should be an angle measure that's getting close to 90 degrees. So take some time to calculate these. Should be fine. Welcome back. Well, perhaps you did some slightly different rounding when you were calculating your angle measures here. That's totally okay. I rounded to the nearest hundredth of a degree. That's fine. But you could perhaps see some confirmation here of some of the stuff that some of the patterns that we saw in the previous slides here. We remember that when we had an angle measure that went from 0 to 90 degrees, sine went from 0 to 1. So you can see that the reverse is also true here. When we have a sine value that goes from 0 to 1, it's getting bigger as it goes down that page. Again, the degree measures also get bigger here. We can see that once again. They're going from, well, you can't really see 0 degrees here, all the way down to 90 degrees at the bottom, but you can see that it's getting bigger. In the same way as before, if you remember the values of cosine, as we went from 0 degrees to 90 degrees, actually went from 1 to 0. So instead of increasing with the degree measure, the cosine value was decreasing with the increase in the angle measure. So as one goes up, the other one goes down. We can see that here again as the value of the as the value of the ratio goes up here from 0.2 to 0.4 to 0.6 to 0.8, the value of the inverse cosine goes, the value of the angle goes down here once again from 78 degrees all the way down to 36 degrees. So again, as one goes up, the other one goes down here. And just like we predicted, when we put in a pretty large value for the tangent of the angle here, we did the inverse tangent of 10 and got an angle value that was pretty close to 90 degrees. So let's actually take a look at an example triangle here in which we've got measures of all three sides here, and let's see if we can calculate all the trigonometric functions for A and for B. Let's just work all of these out here, and in the process find out what the angles are, A and B. So the sine of A, again, that's opposite over hypotenuse, so that's 7 inches divided by 2 feet 1 inch. Yes, I'm sticking some unit conversions at you here. 2 feet 1 inch, that's 14 inches plus another inch, that's 15 inches. All right, so 7 inches divided by 15 inches. That's the value of sine. So the sine of the angle is 0.4667. That's specifically angle A. Let's take a look at the cosine of angle A here. That's 2 feet now over 2 feet 1 inch, the adjacent side over the hypotenuse. That's the relationship that we're working with there for cosine. So 2 feet is 14 inches, 2 feet 1 inch, that's 15 inches. 14 divided by 15 gives us a ratio of 0.9333. Lastly, let's do the tangent of angle A. That's opposite over adjacent. That is 7 inches divided by, well, 14 inches, right? 2 feet, 14 inches. So 7 inches divided by 14 inches, that's 0.5. The tangent of the angle is just 1/2. Let's do angle B here now, and I think you'll notice that there's some similarities between the trig functions for one of the angles on the triangle and the trig functions for the other angle of the right triangle here. So sine B, again, sine is opposite over hypotenuse, but what's the opposite side from B? It's not the 7-inch side. Now it's the one that's on the bottom. It's just to the left of me here. So the opposite side for B is the 2-foot side. 2 feet over hypotenuse, so that's 14 inches divided by 15 inches. And so our sine is going to be 0.9333. What's the cosine of B? Well, again, that's adjacent over hypotenuse, but what's the adjacent side to angle B? That's the 7-inch side now, isn't it? So now it's 7 inches divided by 15 inches. That's 0.4667. Notice that there's a connection here between the sine of angle A and the cosine of angle B. As it turns out, we're looking at the same sides as we go from one of those to the other. We've seen that there's a relationship between sine and cosine, that they're very, very much related, and you can see here why. Lastly, the tangent of angle B, that's opposite over adjacent. Well, the opposite side here now is 2 feet. That's 14 inches, and the adjacent side here now is 7 inches, so that's 14 divided by 7, or 2. This is an angle that has a tangent of 2. So take some time to do this one here as well. You've got some measures of some sides there, and I've actually given you the task of calculating what the hypotenuse is going to be there. So you'll have to use the Pythagorean theorem in order to calculate what that hypotenuse is, but once you've done that, then you should be able to calculate all the trig functions around that calculator. This is also on your activity sheet. Take some time to do that. Welcome back. Well, this involved not only calculating some trig functions, but also drawing upon some previous knowledge with regards to the Pythagorean theorem here. You had to find out the length of that hypotenuse at 15.81. Once you did that, then it was basically just calculating all of those ratios for the sine of A, the cosine of A, the tangent of A, sine of B, cosine of B, tangent of B. You'll notice that, once again, the sine of angle A, the cosine of angle B, those are the same two sides that we're looking at, and so the values of those trig functions are identical. Same thing with cosine A and sine of B. We're looking at the exact same sides there, calculating the exact same ratios, and so we get the exact same numbers for those two trig functions. Also notice that something that I haven't mentioned before, the tangent of A and the tangent of B, what do you notice about those two? Those have a relationship to each other as well. As it turns out, one is the reciprocal of the other. If one is 2, the other one's going to be 1/2. If one is 3, the other one's going to be 1/3, and so on and so forth. So there's a relationship there between those things as well. Let's actually extend this exercise here in which we use some of these trig functions here in order to go from those ratios to the angle measures. Let's find out what the measure of angle A is and what the measure of angle B is. Let's use some of these in order to find out what the angle measures are. So perhaps you're going to use the sine of angle A if you put that ratio in and find out what the inverse sine of that ratio is. You can find out what the measure of angle A is. You could also do it by putting in the ratio there for cosine of A, 0.9488. You can put that in, hit the inverse cosine key, and find out what A is that way. You should get the same answer. Same thing if you put in 0.3333 and hit inverse tangent. You should also get the same answer there. And also do the same thing for angle B. Take some time for that. Welcome back. Well, the fact that I used inverse sine for A and inverse tangent for B was completely arbitrary. You could have chosen inverse cosine for both of them. You could have chosen inverse tangent for both of them. You can choose any one of those three any one of those inverse trig functions to find the angles. You just have to make sure you're using the right ratio that corresponds to the right trig function here. So let's go through one example here, and you don't have to put this into your activity sheet here, although if you want to do this, this is pretty cool here. But this is a good indication of how we're going to be using these trig functions in the next video. You can see here that I've got a single angle here. It's 40 degrees. It's in a right triangle. So there's a hypotenuse shown in green there. That's 20 feet long. And we want to know what's the length of the opposite side in yellow that's given the variable name x. So we have an angle measure, we have a side measure, we want to know what the measure of this side is that's above my head. Once again, we invoke SOHCAHTOA, S-O-H-C-A-H-T-O-A. Well, in this case, which one do we want to be using? Well, we have 40 degrees as our angle here. Do I want to be using cosine? Well, cosine would be adjacent over hypotenuse. I can't use, there's no connection between cosine and this side here that's above my head. There's no opposite in cosine. I could use maybe tangent, because there is tangent is opposite, but it's opposite over adjacent. Opposite over adjacent. I don't know what the adjacent side is, so I can't really use tangent, opposite over adjacent. I can't use tangent, can't use cosine, but if I use sine, that's opposite, it's above me, over hypotenuse. The sine of the angle, so if I can find the sine of the angle 40, that's going to be whatever number that is on your calculator, I can set that equal to x divided by 20. We can use the trig functions to set up an equation and calculate what length x is here. So our equation here is sine of 40 degrees. You can see it in the upper left here. That's equal to x over 20. So let's put in 40 degrees and find out what the measure of sine is for 40 degrees. That's 0.6428. I generally just tend to round trig functions, trig ratios to 4 decimal places. It's just really a habit more than anything. 0.6428, that's equal to x over 20. Well, how do we solve for x? Hopefully you can see here that I just multiply both sides of that equation by 20. Let's remember it's 20 feet, so our answer is going to be in feet. And I get x is equal to 0.6428 times 20 feet, or 12.856 feet. Notice that we can calculate the length of this side to a real high level of precision. If you have a real precise understanding of what that angle is, then you can be pretty precise in your estimate of what the length of that side is. That's something that you can use in a lot of different applications, including construction sites. So hopefully that can be a good solid introduction. It's the first of 2 videos in trigonometric functions that we're going to be working with here, and so take some time. It's important. I always say at the end of these things, it's very, very important for you to go through your activity sheet, highlight the things that are most important in this lesson. I'm not going to ask you to memorize what the values of the trig functions are for each one of the angles. You don't have to know that. You just have to know how to get it on your calculator if I ask for it. But go through and figure out what are the things that are the major themes, what are the things that are most important to remember if I were to give you another problem like the one I just did on the previous slide there. That's the best way to incorporate this information and to put it into practice, both for the assignment and for the exam and for life in general. Oh, John, you're so poetic today. Anyway, I'll see you in class.